Welcome to the session. Greeting of the day. We are in the discussions of the types of sensors, and we have already seen various sensors in the list. Out of that, we are going to see about now in this session the various temperature sensors. In this, what the discussions is, the temperature conveys the state of mechanical system in terms of expansion or contraction of the solids, the liquids and the gases of the system. The change in electrical resistance of conductors and the semiconductors can also be determined here. What then? The temperature sensors such as a bimetallic strip that we are going to see now. The example of bimetallic strip, how this sensor works, that we are going to see now. And then the thermocouples, thermistors are widely used everywhere as a temperature sensors. But now in this example, we are going to talk about this a bimetallic strip, how it helps how this is helpful for our systems. This we are going to know. Now we are going to talk about the first example. A first example of a bimetallic strip here, a bimetallic strip that we are going to see. It is used as a thermal switch in controlling the temperature or heat in a manufacturing process, like we have already given an example of casting, molding, those things. So it is useful there. It contains two different metal strips bonded together. Let us consider a bimetallic strip is there. A motor switch has to be on. When thermal expansion is increased or decreased, the strip may be bent. The strip may be bent and it touches here. So those points we are using in this methodology, we are using in this process. You see, here we have the various setups of one more black color, right? And then one more as a gray scale, one black and one gray scale we have as a bimetallic strip. At high temperature it bends. When it is heating process takes place, it bends. Then what we do, those bending touches the switch, which switch is kept at the bottom last, the magnetic powers. So where it touches, then it activates. So likewise we can able to use this bimetallic strip as a switch also. See, the two metals have different coefficient of thermal expansions that we know. The aluminum having thermal expansions of high, and steel having thermal expansions of less. In such cases on heating, what happens there? In such cases what happens? The two strips bend towards the curved strip. Two strips are going to bend. How it bends? The low expansion material bends in this way. The low expansion material bends in this way, but similarly this high expansion material will bend in this high formant path, right? Which contains here, you see, we have more contact of process where this likewise it bends. Here we have a less radius. Here we have the first we have a less radius and other things have a large then. So how we can tell this we have a thermal coefficient of expansion is high, but similarly we can tell this having a less, this is having a less, right? Having a less. Therefore we are using this combination of bimetallic strips to contrast or expand to act as a switch also, right? We will go ahead. As the strip bends, the soft iron comes in close proximity of a small magnet and further touches the magnet. as the strip bends, the soft ion comes closer. Here we have the magnet at the bottom, and we have here the soft ions of two bimetallic strip. When it is heated, due to thermal expansion, it bends. The lower part having less thermal expansions are bent innerward, and the high thermal expansions enlarges last. This methodology we are using here. So it bends and touches the bottom part of the magnet. Then what happens? It may be activation of the switch, or it may be a deactivation of the switch. Then the electric circuit closes. Then we can see here this electric circuit are closed. So and generates the alarm also, and generates the alarm. In this way you can tell this bimetallic strip process or helps in protecting. The bimetallic strips are helps in protecting the desired temperature. Next we will move further to the next category of this. What in this picture we are going to see about here the coefficient of thermal expansion. Initially I am taking a simple aluminum rod here. A simple aluminum rod has been taken here in such cases. So it is initial position named as L1. Okay, initial position is there named as L1. When the temperature is increased, when the temperature is increased, the original position expands from here to the large sizes. Up to here it expands. Up to here it expands. I am naming it as a L2. Right? When the temperature is reducing, what happens there? It contrasts. This is the expanded position, and this is the original position. And when the temperature reduces, it goes to this original, this L3 position here. This L3 position it goes. In such a way, the expansion of the material depends on temperature. The thermal expansion of the material depends on temperature. Therefore, we are using, therefore we are using this railway tracks. They are using, here. They are using the gap. In the railway tracks, they are using the gap due to when the summers or winters they expand or reduce. Therefore, we are using there. You can see closely. You can see closely this picture. There we have in the bridges we have small gaps. Why? In the summer the bridges of metals it expands. In winter it contrasts. Therefore, we are using those gap to fulfill, to avoid such damages. Okay. In similarly, there also you can see in this tower. In this tower, what we are using by the survey they are telling that this Eiffel Tower increases by 6 inches in summer and reduces in the winter of the same 6 inches. This is what we want to know. Right? So this is there. It all works on the working principle of thermal expansion. The railway tracks, the bridges, the constructions, everything works on the coefficient of thermal expansion. If the thermal coefficient of expansion is high, it expands. Otherwise, if the thermal coefficient of less, it reduces. This content we are using there for the case of expansions. So now we see the second one. You see in this picture, I have utilized for finding those thermal expansion. I have taken two materials. Of one is steel. First one is steel, which is having a less thermal coefficient of expansion. And one more I have taken here as aluminum, which have high thermal coefficient of expansion. So what happens? Which material having high thermal coefficient of expansion expands a large, and when the material which is having less thermal coefficient of expansion like steel, it contrasts or it expands very minimum. That is what I have mentioned here in this video also. A small clip I have included here. You see carefully, a needle, aluminum material has been taken there. Aluminum material has been taken there where it is heated. During heating process, this pointer I have connected there, you can easily carefully you can see the pointer moves as the temperature increases. As the temperature increases, the length also increasing. As the temperature increases, length also increasing. Such cases we are using for this. So this is what I have mentioned clearly here also, the coefficient of thermal expansion. I have compared here with steel and aluminum. So these are the cases I have wanted to tell you. It increases, thermal coefficient of expansion is less, and thermal coefficient of expansion is high for aluminum. Next we go to the next slide. Likewise, so I told you already, aluminum having high thermal expansion and the steel having less thermal expansion coefficient. So now I have, for example, I have taken for the experiment, I have taken one side a steel here and one side a brass here. So steel having thermal expansion less, this brass having thermal expansion as high. These are the things that we want to note it down. So thermal expansion this side has high, thermal expansion this side is low. Now I am going to combine these two. Now I am going to combine these two. Now I am going to combine these two for our understanding. So what happens? It should bend. In which direction it should bend? It should bend in this way. So thermal expansion of brass I have taken here. This brass I have taken. This side I have taken steel. Okay, I have combined two strips here in this way. These two strips I have taken one strip, and I have simultaneously I have taken the second strip also. So in which direction now it should bend? It should bend in this way. It means it's bending in this lower part, because this having less thermal coefficient of expansion, this side having high thermal coefficient of expansion. So what happens? It bends towards the less thermal coefficient of expansion. That is what the picture or video also showing here. You see, I have one side less, one side I am having high. Therefore, it bends over the other. The upper image showing here is I have started heating. I have started heating there. When heat is increasing, after the material is absorbing, what happens? It is start bending. This methodology, other end, when it is bending and I am using it to go, I'm going to have a switch there. It touches, that I am going to use. Right? You see now. You see. So now we understand it is bending due to thermal expansions. Now what I am having here? This bimetallic strip I have connected to an iron box now. The bimetallic strip has been prepared. But I am the same thing I am connecting now to the iron box. What happens? Let us understand before going to the iron box. Let us understand the concept first. You see here, the strip has been taken, the strip has been connected, and the circuit has been closed here. Now it closes, the circuit power goes in. If the power goes in, the electricity, the heat generation will occur there. If the heat generated occurs, what happens? Obviously, the bimetallic strip will start bending. The bimetallic strip start bending. So it start bending means towards the low contraction coefficient of expansion, it bends there. So what happens? It bends like this. There you can see the image, the animated I have attached here. It disconnected. The circuit has been disconnected here. You see, the circuit has been disconnected. Circuit has been disconnected. The strip moves up. Due to the movement, the circuit has been removed. That methodology I am using here. What I did here, you see, what I have did here, the same iron box, I kept this bimetallic strip at the center, and then the circuit has been closed now. This condition I have did here. It has been closed. Right? When it is started heating, it start to remove upward direction, and this connection will not be there. Iron box will not be heated. When the temperature is reached, it may be high or low. According to that, we have to give pressure over the strip. We have to give pressure here. You have to give pressure here over the knob. The knob will be there. You have kept and we have connected. We are pressing. If the temperature is, we can able to terminate the switch also. Right now, we know we have taken the bimetallic strip, and the bimetallic strip has been connected, and it is supply has been given, and then it is ready for the connection. When it is heated, it increases. When it is heated, the strip moved upward. That we know. That we have taken there and kept here in the iron box. How it works now? How it works now? You see? Now I have taken the iron box, the knob. See, this is the knob here. I have taken the knob and I am keeping here. I want to rotate. I want to give more pressure there. I want to give more pressure in the knob. How we are giving? The knob, usually we have seen this. We have seen the green color knob here. You see? The green color knob I have mentioned there. In this knob, a light pressure has been applied. The green color indicates it is having a light pressure. So what happens? What happens in the circuit? In the circuit, the bimetallic strip has been pressed lightly. Then until the pressure, heat has to overcome and it moves upward. Even though it will also move and it is going to disconnect. But it takes time in the green. How much? If it is ideal condition, it may be heat may be generated in a minute. But I am giving a light pressure over the bimetallic strip. It has to overcome this pressure and then it is to move upward. So that what it is happened there. Look carefully. Look, see carefully there. The pressure has been applied and it opens up when it is read. Now, I need more heat there. I need more heat there. I am giving more pressure here. See, I am giving more pressure from green. I am increasing the pressure. I'm increasing the pressure here. Right? So what happens? It has to overcome those more pressure. It means more heating required, more bending has happened. So in this condition, I'm drawing here. In this condition, it is a green color. I have given the pressure here lightly and the circuit has been closed When the heating occurs there, when the heating occurs, it bends upward direction. But in the case of here, I am pressing, giving more. I am giving more pressure here. Double the pressure of this one. Double the pressure of this one has been given. So it should overcome more pressure here. It should overcome more. Then it can able to move upward. So that is what this image has been showing. That is what this image I have represented, that after red color and orange color you can able to differentiate. Orange shows a light heat, red shows the more heat absorbed by the bimetallic strip. Okay. Now what we understand from here, the switch has been started, the pressure has been given. If it is light, if it is very light, according to the light heat generated. If I instead of ironing the silk cloth, if I want to iron the cotton cloth, I am increasing the pressure on the knob. If the pressure is increased on the knob, what happens? It absorbs more heat. That is what I have represented here in this image. The red color increases. That is what our understanding up to now. Right? Now what I am doing here again, so simple conversation we can understand from this. Simple conversation, we have seen an iron box with the red color light blinking and off. The light blinking indicates the circuit has been closed. The light blinking indicates the circuit has been closed. It means the circuit has been closed, therefore the circuit goes for the light. Right? Here we have the bimetallic strip. Here at this point we have a bimetallic strip. It is closed now. This image represents the same. Here we have this, at this point we have the bimetallic strip which is closed. But what happens here? What happens here? Here the same bulb we have taken, but after heating process it opens up. This is not there. This is not there. So if it is not there, circuit is not closed, then light will not blink. Light off. Light is off, in the off condition. So this is how we can take when the circuit is closed. For example, by using the bimetallic strip, I am telling. When the bimetallic strip is not absorbed heat, it is in circuit. We are using for switching on, switching off. So therefore, in circuit, the light blinks. But the same content, when the heat bimetallic absorbs the heat, it opens up here. It opens up here. Therefore, the power circuit is not closed, therefore light will not blink. Now how we are using this? We are using this as a switch. I am using this as a switch, bimetallic strip as a temperature sensor, use it as a switch here. From this picture, we understand that the switching on and off is application of bimetallic strip. That we understand now. Now see, out of bimetallic thermometers are there to measure the fluid or temperature or pressure there. So how it happens? You see, I have used here a bimetallic strip. I have used the bimetallic strip in the tube and have kept inside, and it is connected over the pressure gauge, a temperature measurement gauge I am using, right? So you can see this animated picture. You can see this animated picture here, that what happens, I am heating at the bottom. The same thing I am heating at the bottom. Due to the increase of heat, the bimetallic strip also expands. The bimetallic strip also expands. Those as expansion is connected to here I have. So I am heating here and it is connected over to the point. So I think you understand. So I connected here. The strip is there, the bimetallic strip, and this point is connected to the gauge. So what happens when it is heated? When it is heated, the bimetallic strip expands. By this expansion, the strip of pointer which having the pointer which moves here and there. So that is what we have used at the bottom of the animated, which shows you clearly. Outside you see the expansion of the material and temperature has been measured over the other end, right? So I am telling this case as a bimetallic thermometer where the heat is converted into the mechanical actions, where this heat giving on the strip converted into the, on the dial it is converted into the mechanical motion. From the strip it is converted to the mechanical motion, it rounds. Okay, that is how we understand this point of bimetallic thermometers. Now I want to use the temperature sensors in liquid also. We have used already, we have seen this mercury thermometer. This mercury having a same properties of high coefficient of thermal expansion, that we are using. So and also having high boiling point. So at the maximum temperatures we can use this. So these are one of the example of temperature sensors of mercury liquid thermometer we are using. So in earlier cases we have seen here as a bimetallic thermometer, which the same temperature can be utilized. But see, again I am using this of a liquid thermometer also. It is possible to use there. The number 1 point, high thermal coefficient of expansion for the mercury, and also high boiling point for the mercury. Therefore we are using this mercury inside the strips to measure the temperature also, right? So the thermistor, now one more content is there regarding thermistor's electrical resistance content. It follows the principles of what follows. It decreases its resistance. It decreases its resistance. It decreases its resistance. It decreases its resistance. Increase in the temperature as the increase in the temperature. So this one as increase in the temperature. The temperature increase occurs there. You see, the temperature increases. Obviously, what happens? The resistance reduces. This methodology we are using now for the thermistor. The material used in thermistor are generally as semiconductors. Semiconductor means when the heat increases, it's conduct current. If the heat reduces, it's become the insulator. That idea we are using here. The materials such as sintered metal oxides, mixture of metal oxides, we can able to use along with the chromiums, cobalt. So such cases we can able to use the doping also we should do around there. So how we are using? We are taken two materials of silicon and boron. Okay, and these are both are combined to make a semiconductor device which acts having a high resistance, but when it is heated here, it loses its resistance. That is what I have mentioned you. The temperature increasing, reduces the resistance. This we are going to use in the next one. You see, so now what we have understand, the temperature increases, resistance reduces. This we are going to use now. So as the temperature of semiconductor material increases, the same point, as the temperature of semiconductor material increases, the resistance reduces in the semiconductor and then a number of electrons able to move. The same point what I told you there, I have one conducting material here and I have one more conducting material on the other end. Now I am using one semiconductor in between, and therefore there is no contact between conductor 1 and the conductor 2. Now what happens? Now I am heating this, material. Now I am heating this. Due to the heating process, what happens? You see, this semiconductor become the conductor, like C3, C1 conductor 2, and this is already semiconductor material. When I am heating, giving to the temperature increase, the semiconductor resistance reduces. Therefore, the electron flow will happen from here to here. Therefore, I am conducting now. I am conducting this circuit here. I can able to connect a circuit and forms. So see, the same circuit which is available in the iron box also. So these things we can able to use. So this results in increasing the current flow. This results in increasing the current flow of the material. So the change in resistance identified as a temperature change. So what happens? This resistance is measured. This resistance we are going to measure out. This is calibrated one. Which one is a calibrated? So when this resistance changes occur in the system, through the pre-programmed conditions, we can able to measure this resistance change and find. We are using digital thermometers to measure our temperatures when we got a fever. Those things all works in these principles. So now we move to the next one, right? So what we understand now, the change in resistance we are going to measure from the calibrated condition. The change in resistance due to temperature increase we are going to measure from the calibrated condition. So now I have taken a digital thermometer that we have already seen. So this one we have already seen, a digital thermometer, and then it is connected. You see here it is a current flow is there when there is no temperature. I am writing here, when there is no temperature here. See, there is no temperature belongs to 0. When the temperature increases, see this one, when the temperature increases there, the resistance start reducing, current flow is high. See, the resistance start reducing and we are getting 2 points. So where we are using this digital thermometers, we are using to measure the temperature of the body. We have each and every home we have this, where in the fridges, in the ACs, refrigerators, microwave ovens, all examples belongs to this thermometers we are using. All these examples we are using in day-to-day life. We are controlling the temperature of the AC. How? We are controlling the temperature of the fridges. How? We are using this small thermometer inside. So this is how we can able to understand this applications of thermometer to measure temperature sensor. Right. Now we have seen a number of examples of bimetallic strip, liquid thermometer, digital thermometer. So from the iron box to washing machine to the AC, we have seen some examples. Now let me move to the next one. So in this graph, I want to represent you a few points there. From here you can able to see at the x direction we have a temperature. A temperature is keep on increasing. As the temperature increases, what happened to the resistance in the y direction? It keep on reducing. So how it moves there? It moves like this. It is the xy direction where we have a temperature here, and then here the resistance. As the temperature is keep on increasing in this direction, the x direction, the resistance keep on decreasing like this. So what happens in case if you are taking the semiconductor, here it at this temperature it is an insulator. At this case it is an insulator. But same when the temperature is reduced at this stage, it will become what happens? It become a conductor. It become the conductor. Here it is insulator. Here it is conductor. Such a way we can use these applications of thermistors. Right? You see, now we can understand the difference or comparison between the temperature change and the resistance change which we are using for the thermistors. Right. Therefore, we came to the end. The application of these thermistors where we are using, we can able to monitor the oil and the coolant temperatures, whether it is increases or it decreases. We can able to monitor the temperature of the incubators. We can able to monitor the temperature of batteries. In the mobiles we are using, increasing of the batteries or decreasing, small content of this able to temperature can able to measure. To monitor the temperature of a hot 3D printer pointer, we are using a tool, right? Those tools we are using to manufacture the product. How much temperature of this tool is there? These thermistors are attached there to find how much temperature at the end of the tool. Maybe welding process temperature can be measured in the field. Likewise, to maintain the correct temperature of the food we have it. Now only we have seen the oven as an example. So those ovens are food applications we can able to consider, like the toasters, the coffee makers. There and all we can able to use. So same example what I told you they have written here as a refrigerators and freezers, hair dryers, everywhere. The temperature, wherever the temperature involves, these thermistors, the thermocouples, the bimetallic strips, all will be involved there. The important concept you should have understand. So you see next one. We came to the summary up to now what we have seen. So what we have seen here, you see, we started the class with mechatronics, and we have given an introduction of what is a domain, right? And then we have given an introduction of elements of mechatronics. Then later we have given about the design of mechatronic system. Then also we have seen about the various closed loop, open loop, open loop systems. These things we have seen as a part 1. This one we have seen as a part 1 in the system. Later, and also open loop, closed loop, and also we have seen about sequential control. By this we have seen some examples for everything. We have seen some examples everywhere. The working examples we have seen. So in part 2 what we have seen, you see, this is a part 2 content. What we are going to see here, we have already seen about the part 1. This is about part 2. Right. In part 2 we have seen about this different types of sensors. Probably 6 to 7 sensors we have seen. First for the displacement sensors and position sensors, we have taken the example of finding the potentiometer number 1 and the LVDT number 2. Such examples of types of sensors we are classifying. In the part 1 we talked about the mechatronics. In part 2 we have talked about types of sensors. So there are the list of part 2 contain this types of list of sensors. There at the first one and the displacement portion we have seen the potentiometer and LVDTs, and also the capacitive sensors, the strain gauges. Such cases we have seen. And later in the velocity sensors, what we have seen there, in the velocity sensors we have seen about the tacho generators, and optical encoders. So tacho generators and optical encoders as a types of sensors. Then about in the force measurement system, the same strain gauge system can be used for displacement, and also the same strain gauge system can be used to identify the force, pressure also. And also we have seen about the tactile sensors, piezoelectric, important topic of reverse piezoelectric effect, a piezoelectric effect for titanic falls, right, snowfalls, measurement of radars, underwater ships, those things all comes here, right. And then also we have seen about this fluid pressure, how we are measuring this one, the fluid pressures. We have used about the Bourdon tubes. We have seen one animated video also here, some Bourdon tubes, the diaphragms, the capsules and billows. So such cases are we have used. So these cases are we have used for liquid level management. So I am listing out the various types. The liquid level management, how we have measured as a water tank and Hall effect, the EMF generations, the Hall effect sensors we have used. We can able to understand the Hall effect sensor. This we have used for the various lastly at the light sensors for a photoelectric sensor. So see, so these are the various types of sensors we have seen in this topics of introduction to mechatronics. So introduction, which contains all the parts of mechatronics, closed loop, open loop, sequential, everything. And the part 2 contains about the different types of sensors classifications of 7 to 8. In these 7 to 8 classifications, we have 2 to 3 types. Maybe nearly we have concluded about 15 types of sensors we have seen. Okay. The remaining part of the mechatronic systems will continue in the next session. Thank you.